Okay, the final type of spectroscopy that you need to know about is NMR spectroscopy. It splits into two different categories. So you have what's called proton NMR, which is looking at the hydrogens, and you also have carbon NMR, which is looking at the carbon atoms, and you use the carbon-13 isotope in order to do that. So we'll look at carbon NMR first. So let's imagine we've got a molecule that looks like this. Let's do this molecule here. So it's a ketone, it's pentan-3-one. Now NMR is the best technique really. It gives you the most information and usually is the least complex as well in terms of how you get the information from it. So pentan-3-one, the carbon NMR spectrum would look something like, let me just make it first. So the carbon NMR spectrum for pentan-3-one would look something like this. So we need to be able to work out why it would look like this, what do these different peaks mean, and what does the axes mean. So first thing, the axes. So this delta symbol stands for chemical shift. So what you're doing is you're measuring the chemical shift of some different things inside this molecule, and these units here are in parts per million. So the x-axis is chemical shift and it's measured in parts per million. Y-axis is just intensity. They don't tend to draw it, they just tend to give you the x-axis and then some peaks off it. So why is it that the spectrum looks like this? We need to look at something called carbon environments in order to do that. So the number of different carbon environments will give you the number of peaks. So just bear with me for a minute. Number of carbon environments is number of peaks. Type of carbon environment will give you the position of the peaks. And then the height of the peaks tell you number of carbons in same environment. So number of carbon environments is the number of peaks. So in this spectrum I have 1, 2, 3 different peaks. That means I've got 3 different carbon environments. The type of carbon environment is the position of the peak. So as the chemical shift changes, it shows me I've got different types of carbons in different environments. And then the height of the peaks is how many carbons in the same environment. So these two have the same height, therefore there's the same number of carbons in this environment as there are in this environment, and then this peak is half the height, so there's half as many carbons in this particular environment. It will make more sense as we get stuck into this structure now. So in order to be in the same environment, the carbon atoms have to be bonded to exactly the same things in exactly the same way. So bonded to same things in same way. It has to be exactly the same things in exactly the same way. So let's pick a carbon. If we pick, say, this carbon here, and we're going to label it carbon A, we've got to look inside our molecule and we've got to think, are there any other carbons in there in the same environment? So bonded to the same things in the same way. So this carbon here is got 3 H's attached to it, and let's look how far it is away from it. The oxygen is 1, 2, 3 away from the oxygen. So that's what we're looking for, something in the same sort of environment as that. This one has got 2 hydrogens by it, a carbon and a carbon, so different environment, those aren't in the same. Same for this one, so it's got no hydrogens attached to it, so I can rule that one out. The one that matches is this one over here, so this is also carbon A, it's in the same environment. So it's got 3 hydrogens attached to it, same as that one, and it's bonded to everything else in exactly the same way. If I'd say this one's carbon B, looking for something else that's bonded to the same things in the same way, so 2 H's, 2 away from an oxygen, 1 away from a CH3. This one here, 2 H's, 2 away from the oxygen, and 1 away from a CH3, so bonded to the same things in the same way. That one's B, and then this one is the only one left over, which is C. So I've got 3 different carbon environments. That's why I've got 3 different peaks. So number of carbon environments gives you the number of peaks. Then the position of the peak is dictated by the type of carbon environment. So if you look in your data booklet for a carbon that's part of that's got a double bond O attached to it and is a ketone, you'll be able to see that the peak should be between 190 and 220 parts per million. So that carbon there is a ketone carbon. There it is on my spectrum. So that is carbon C. Carbon B. So carbon B is 1 away from a carbon-oxygen double bond. So if you look in your data booklet, you'll be able to see, I think it's 3 down, there's a peak between 20 and 50 for a carbon that's neighbouring a carbon-oxygen double bond. So that's there. That should be this one here. So that's carbon B. And then carbon A are these 2 here, which should be, if you look in the data booklet, between 5 and 40 parts per million. So this one here is carbon A. Why are these 2 peaks twice as high as this peak? Well, if you look, we got 2 carbon A's, so the peak is too high. We got 2 carbon B's, so the peak is too high. And then we got 1 carbon C, so the peak is 1 high. So the relative heights of the peaks, these 2 should be twice as high as this peak here. So I think it might be worth doing another example of one of those. Let's do an ester. So let's do something that looks like this. O, C. We'll do an awkward one. So let's do this. You don't need to be able to name this ester, but you could be asked to predict what the carbon NMR spectrum would look like. So this is the ester. What does the carbon NMR spectrum look like? So first thing I would do is pick a carbon. So let's call this one, I'm going to change the colour now. This one is called carbon A. I got to look in this molecule, is anything bonded to exactly the same things in exactly the same way? These aren't, they're nowhere near these oxygens. This is 1, 2 away from that oxygen, whereas this is 1, 2, 3, 4 away from that oxygen, so there's no chance. Nothing's the same as that. Nothing's the same as this one. That's on its own. If we say that one's carbon C, is anything bonded to the same as that? The only ones you'd be tempted by are these 2, whereas this carbon B is double bonded to an O, this one isn't. It's single bonded to an O, but not double bonded to an O, so completely different environments. There's loads of reasons why they're in different environments. If I label this one D, hopefully you'll be able to see that this one and this one are also in that same environment. So let's see how far they are away from that oxygen. 1, 2, 3, 4. 1, 2, 3, 4. And this one, 1, 2, 3, 4. You can count them away from anything, so you can count it away from the CH3, from the O, anything. They're going to be bonded to exactly the same things in exactly the same way. So in terms of how many peaks we'd have in this spectrum, we'd have 1, 2, 3, 4 different peaks. 1 because of a carbon A, carbon B, carbon C, and a carbon D. We've just got to work out where they are and how high they are now. So So we've only got one carbon A, so the peak would be 1 high. 1B, so it would be 1 high. 1C, so the peak would be 1 high. And then we've got 3 Ds, so the peak would be 3 times as high for this carbon than all of the others. In terms of positions of the peaks, go back to the data booklet, got to go work it out. This one would be between 5 and 40 parts per million. This one here would be between 50 and 90 parts per million. Carbon B is part of an ester, so you'll be able to see it on the data booklet written as ester in brackets. It's between 160 and 185 parts per million. And then carbon A, which is this one over here, is next to a carbon oxygen double bond, so it would be between 20 and 50 parts per million. So drawing the spectrum, 0, what do we need to go up to? 200, there's 100, chemical shift in parts per million. I'm going to have a peak that's 1 high between 20 and 50, so let's do it about there. I'm going to have a peak that's 1 high that's up around here. I'm going to have a peak that's 1 high between 50 and 90. And then I'm going to have a peak that's 3 high between 5 and 40. So somewhere down here, but it'll be 3 times as high. So that's what the carbon NMR spectrum for this ester would look like. Okay, so that was carbon NMR. We're now going to do proton NMR or hydrogen NMR. It works very similarly. So if you can master carbon NMR, hydrogen NMR is very similar principles. So the number of peaks is the number of hydrogen environments. The position of the peaks is the type of hydrogen environments. And then the height of the peak is the number of hydrogens in the same environment. So let's pick a molecule. Let's do an aldehyde. So if we do butanal, it would look like this. So in order for the hydrogens to be in the same environment, they've got to be bonded to exactly the same things in exactly the same way. So I'll start over here. Let's call this one hydrogen A. I've got to decide, is there anything bonded to exactly the same things in exactly the same way as that hydrogen? Well, no. So there's just one of those. If we call this one hydrogen B, is anything bonded to exactly the same things in exactly the same way as hydrogen B? Well, yes, that one is. Now, some people will be tempted to say these two also are. So they've got to be bonded to exactly the same things in exactly the same way. If we look how far they are away from that oxygen, this hydrogen is 1, 2, 3 away, whereas this one is 1, 2, 3, 4 away. So not in the same environment. So there's 2 HBs. We're going to call these 2 HCs. And there's 2 of them. And then these 3 are all in the same environment as well. We'll call them HD. So there's 3 of those. So HA is going to be 1 high, because the height of the peak is the number of hydrogens in the same environment. So 1 high. This one's 2 high, this one's 2 high, and this one is 3 high. We've just got to work out the positions of the peaks now. So let's start with the HA there. That's part of an aldehyde. If you look in the data booklet, it should be at 9.8 parts per million. HC is these 2 HB, sorry. I've done it the wrong way around. That's why. 9.8 parts per million. So we're going to cross now. HB is next to a carbon oxygen double bond. If you look in the data booklet for one of those, you'll see they should be between 2.0 and 2.5, or no, 3.0 parts per million. So that's for that hydrogen there. HC should be at 1.3 parts per million. And then HD should be at 0.9 parts per million. So if I was drawing that spectrum, zero, highest number is around 10, chemical shift in parts per million. HA is 1 high at 9.8, so right at the top, 1 high. HB is between 2 and 3, so that's about 5, 2 and 3 would be about here. And it's 2 high, so twice the height. HC is at 1.3 and it's 2 high as well, so same height as this one, so let's say it's about there. And then HD is at 0.9 and it's 3 high, so much higher. Again, it's probably not that accurate, but hopefully you get the idea. So this one's 1 high, these two are 2 high, and this is 3. This is HA, and we've got HB, HC, and HD.